Hello and welcome to Pep Talk with me, Mr. Pepperell. In this episode we'll be asking, what are stars, where did they come from, and where are they going? By the end of this video you should be able to tell me, what are the stages in a star's life, what will eventually happen to our local star, the Sun, and exactly what is a supernova.
So this is one of my favourite sights in the night sky. It's the constellation of Orion, and what we can see here is this bright orange star here is called Betelgeuse or Betelgeuse, depending on how you all pronounce it. That's one of Orion's shoulders. We've got another bright star here, which is Bellatrix. That's his other shoulder. We've got some stars down here, which represent the knees, and we've got these three distinctive stars in a row here, which are Orion's belt. And hanging down here below his belt is Orion's sword. And there's something just here in Orion's sword that I'm quite interested in. So if we zoom in on this little tiny object here, you can actually see that with your naked eye. If we zoom in on it, this is what you can see, and you can see this with a decent pair of binoculars or a small telescope. And this is actually called the Orion Nebula, and this is a vast cloud of gas and dust, and it's what we like to think of as a stellar nursery where new stars are born, and the heat from these new stars is causing all this gas to glow with the heat they're producing. But how exactly are all these new suns born? Well, to find that out, we need to work our way through this diagram, starting up here with this big cloud of gas and dust, which was the nebula that we just saw, okay? And the particles in these big clouds of gas and dust, which are mainly hydrogen, okay, as they float about in the endless void of space, they're slowly but surely attracted to each other by the tiny gravitational forces between each of the little particles, okay? They exert gravitational attraction on each other, and they gradually draw each other together, and our cloud of gas slowly starts to collapse due to its own gravity, okay? And as it starts to collapse, what happens is the centre of the cloud starts to heat up. And the cloud continues to collapse, and it begins to get hotter and hotter, and it gets denser and denser in the centre of it, and what we get forming is something called a protostar, or the start of a star, okay? And as the centre of this cloud starts to heat up even more, when it gets hot enough, the light nuclei that are in it gain enough energy, enough kinetic energy, that they can finally overcome the electrostatic repulsion that they feel towards each other, and finally nuclear fusion that can occur, that we've talked about before. Okay, and when this nuclear fusion occurs, a lot more energy is released, and the centre of the cloud becomes hotter and brighter until eventually nuclear fusion is taking place, and our star is born there. So we've got a brand new star being formed at the centre of this cloud of gas and dust, which is collapsing on itself due to its own gravity. Okay, now it's time for our young star to settle down now. Okay, and still floating around, we've got all the leftover gas and dust which didn't form the core of the cloud and turn into the star, and this is what we refer to as a protoplanetary disk, okay? And all this leftover material that didn't form the star continues to spin around the new sun in a protoplanetary disk, and eventually this leftover material will coalesce, or it will stick together into little tiny hard lumps, and those hard lumps will bump into other hard lumps to form slightly bigger hard lumps, and eventually they'll all merge together to call what we call planets. And in fact we live on one of these little lumps, and we call it Earth. So our star is now entering something called the main sequence, where it's going to stay for most of its life, and during this time the radiative pressure, which is released by the fusion in the core of the star, the energy being given out, is forcing the star outwards, but at the same time that outward force is being balanced out by the force of gravity, which is trying to make the star collapse. Okay, so the star that we've got here is basically an enormous explosion which is being sucked back in at the same rate as which it's flying out. Okay, so our star is in the main sequence, and this is where it's going to stay for most of its life. As long as it's got hydrogen to fuse into helium, it's going to be causing this outward pressure, which is going to balance the inward force of gravity, and it will stay in its main sequence. Now, the main sequence of a star lasts for millions of years, and our own sun is about 5 billion years old now, and it's going to keep fusing hydrogen for about another 5 billion years yet, so we haven't got to quite worry about it running out anytime soon. Okay, but of course, it can only stay stable as long as it has actually got a supply of hydrogen, and it can carry on carrying out nuclear fusion, and the forces within the star stay balanced. But what happens when this hydrogen runs out? Well, the fate of the star depends very much upon its mass. Now, although the Sun is obviously pretty big, our star is actually considered to be a low mass star. Okay, and when low mass stars run out of hydrogen in their cores, the outward pressure caused by nuclear fusion stops and the core of the star begins to contract due to the gravity. Okay, and as it contracts, it's heating up as it does so, and eventually the core becomes so hot that it can start to fuse together the helium that was produced in the original fusion. Okay, so it can start to fuse together heavier and heavier elements. Okay, and we're going to look at that in a whole separate video. But while this happens, something else is going on as well. Okay, the remaining outer layers of the star are starting to cool and they're starting to expand, and they turn red as they do so. Now, the star that we saw in the constellation of Orion at the start there, the orangey coloured star, that's one of the stars we're talking about now. It's become a red giant star. Okay. The core of the star is still really hot. There's still fusion going on inside there, but the outer layers of gas are cooling down and they're starting to float away, and the star's looking a lot redder. Okay, now eventually the core contracts again due to gravity until it has reached about the size of our planet, in fact, so much smaller than the original star. And when it gets to this stage, it can't contract anymore. Okay, it's now really hot, obviously still, okay, and it's really dense and it's solid, and it continues to glow just because it's so hot. So it's out there glowing in space, and it's become what we call a white dwarf. Okay, now eventually, because there's no fusion taking place, it will start to cool down and it will start to fade away, and eventually it will turn into what we refer to as a black dwarf. Okay, and the remaining gases are ejected into space and they form a planetary nebula that will eventually contract and form new stars again. So that's what happens when we get a low mass star. So that's what happens with the low mass stars, but what about the big boys? Well, if a star was big enough to start with, and by big enough I say about 1.4 times the mass of our Sun, it goes through a similar process, okay, but this time we get a much bigger red giant being formed. We get what's called a red supergiant being formed, okay, and the core keeps getting hotter, and in a red supergiant it can fuse together larger and larger nuclei, okay, and we're getting much bigger nuclei, all the way up to the nuclei of iron atoms being formed, and again we're going to look at that in a later video, okay, but eventually fusion can't carry on forever, and the core will finally start to collapse, and when it collapses all the way in, it bounces, and suddenly it will explode outwards in what we call a supernova. So our star has run out of fuel up here. We've got no more energy being released as a result of fusion. So gravity has won. The core of the star has collapsed, and the outer layers of the star have bounced off the core in this massive explosion called a supernova, releasing all this energy. Okay. What happens next to the core of the star that's been left behind depends very much on how big it was to start with. So first we're going to look at what would happen if the star was somewhere between 1.4 times the size of our Sun and 3 times the size of our Sun. Okay, now if it was about this big to start with, what would have happened is, okay, as the supernova occurred, the core would have been compressed so much by the explosion that the electrons of the atoms in the core would have been forced into the nucleus of the atoms, okay, and this would have turned the protons in the nucleus into neutrons, and we would have had what we call a neutron star being formed. We've got a neutron star here, okay. Now a neutron star is a ludicrously dense object in the universe, okay. 1 teaspoonful weighs about as much as a mountain, which is about 10 billion tons. Okay, and the neutrons in this star cannot get any closer together, okay, so the contraction of the nucleus has to stop here, and we're left with a ball of neutrons. It's probably about 20 kilometers across, which is not really very big considering how big the star was to start with, and sometimes they're spinning around and they're giving off these beams of radio waves and pulsing off into space, so sometimes we call these things pulsars. Okay, so that's if the star was about 1.4 times bigger than our Sun. But what about with really big stars? Well, if our starting star was greater than 3 times the mass of our Sun, when its core collapses, not even the neutrons can resist that gravitational collapse, okay? And the neutron star that we saw, that's where the process stopped, okay? That neutron star continues to collapse into an infinitely dense point called a singularity, okay? Basically, a black hole has formed here, okay? It's just collapsing in on itself, squeezing itself smaller and smaller, denser and denser, and that keeps on going to a single point called a singularity. Now, a black hole that we've got there by that little black dot, okay, is an object so massive that nothing can escape its gravitational pull, not even light. Hence that's why it appears black in space. We can't actually see them because they're black against the blackness of space. Okay, and at this point all known laws of physics break down and cease to exist, and reality as we understand it no longer exists. Okay, so black holes probably aren't going to be in the exam. As long as you know how they're formed, you're not going to be asked to talk about the physics of a black hole. So here we can see a quick summary of those processes we've just talked about. We've got a stellar nebula at the start here where new stars are forming as that cloud of gas collapses in and heats up on itself. Okay, if the star is an average size, quite a small low mass star, eventually when the hydrogen runs out, the core will start to collapse, the outer layers will expand and cool down, we get a red giant being formed, and eventually the outer layers will drift off, forming a planetary nebula that can form new stars, and the core will form a white dwarf, a glowing hot ember basically left from the star, which will eventually cool down and fade away. If we had a more massive star, okay, the same process, the core starts to contract, fusing into heavier and heavier nuclei, creating new elements. The outer layers will drift away, again forming a planetary nebula which can form new stars, but eventually the core will contract when fusion stops, resulting in a supernova, a massive release of energy. If the star was about 1.4 times the size of our sun, we get a neutron star, as the entire core is converted into neutrons and we get this ball of neutrons, incredibly dense left. If it was about 3 times the size of our sun or bigger, we get this whirly swirly looking thing over here. They don't really look like that, but we get a black hole, which is an object so dense that nothing can even escape it.
So that's everything we need to know about protoplanetary disks and black holes and the life cycle of stars. Any problems with that, don't hesitate to tweet me at Mr_Pepperell or email me and I'll get back to you ASAP. Thanks for stopping by.